Hello, Prof. Moore here. Let's define Bronsted-Lowry acids and bases, which is a subtopic under acids and bases. What is a Bronsted-Lowry acid? A Bronsted-Lowry acid donates a proton. Supposed to donate a proton. It's just a proton donate. It gives a proton. A proton is hydrogen that's partially positive, lacks some electron density, or it lacks some electron presence, and also it could be completely positive, where there is no electron at all. Those are protons. So let's take an example of a compound, a molecule like ammonia, and then let's react that ammonia with an acid like HBr, hydrobromic acid. I'll show the lone pairs here, but I'll have you know, once you're given these two and you want to predict what will be formed, that's what this arrow says, yields products. These are reactants to yield products. If you want to predict that, you have to decide who plays which role. Now, I'll start with the HBr. It seems to me that bromine is the most electronegative. Remember that electronegativity increases across the periodic table and up. So left, right, then down, up. So bromine is somewhere here. So bromine should be the most electronegative of the two between nitrogen and bromine. It takes electrons towards itself strongly. That's what electronegativity means. It is having more electron affinity. So this hydrogen will be more positive than the hydrogens on nitrogen. This is expected to be the acid, because we are looking for the best proton to be donated between the two participants. It's gonna donate that hydrogen. This is dipole moments. We discussed that in an earlier lesson. So HBr will play the role of an acid, and in that case, ammonia will play the role of a base. Now the nitrogen has a lone pair. That lone pair will be used to steal, to grab, to take, to bond to the hydrogen. So ammonia here is going to play the role of a base. It's going to be the proton acceptor. And that's going to be defined down here as Bronsted-Lowry bases. Ammonia will be the Bronsted-Lowry base in this case. So we are pushing this arrow again using two-ended arrow, double barbed arrow showing two electron movement or transfer. So we are making a new bond. We are making a new bond between the hydrogen and the nitrogen. So let's draw what we will get. In the product side, we will get the ammonia that is modified. There's no more lone pair because it's hiding in the bond. A bond is made of two electrons. This nitrogen will get a plus charge. Remember, formal charge of nitrogen equals to the valency of nitrogen is 5 in the periodic table. Subtract number of non-bonded electrons. There's no non-bonding electrons. There's no lone pair. Subtract number of bonds. You get +1. What happens to the bromine? In the mechanism, which is the arrow pushing process, the two electrons between hydrogen and Br would be thrown to bromine, because bromine, it's mean. It wants to grab those electrons from the bond. So the bromine will have now 8 non-bonded electrons or 4 lone pair of electrons. Bromine, like fluorine, chlorine, and iodine, is in group 7, main group 7 of the periodic table, which people would call overall group 17. So it has a valency of 7, but now it has 8 electrons on it. With the extra electron, it will get a negative charge. If you want to do the calculations, formal charge of Br has a valency of 7. It is in main group 7 of the periodic table, excluding the transition metal elements. and then you have 8 non-bonding electrons. There's no bond, you get -1. That's a justification for that charge right there. Okay, so this will be the product, this will be the reactants. Ammonia accepted the proton as HBr donated the proton, so this is going to be the Bronsted-Lowry acid, and ammonia that accepted the proton will be the Bronsted-Lowry base. Okay, so that's what we are defining down here. The ammonium ion here is going to be the conjugate acid because it came from the base, and then the Br is going to be the conjugate base. It came from the acid, and it's a base because of the negative charge. This is an acid, of course, because you have a positive charge, which is an indication of an acid. I'll give you another example. I've already defined what a Bronsted-Lowry base is. It's a proton acceptor. But I'm going to give you another example of a Lowry base. So let's say this time we have acetic acid, which is the active ingredient in vinegar. And then I'm reacting that with OH minus. The negative charge here again suggests that this is going to play the role of a base. And this acid is acidic because of so many dipole moments in the molecule, making it more positive because electrons are sucked out of its presence. Negative and positive charges attract, so I would expect that this proton would be stolen by OH minus, and then these 2 electrons will be thrown onto the oxygen, which currently has 2 lone pairs. So this is going to play the role of an acid because it is a proton donor. This is a proton donor. And the base is accepting that hydrogen. This is going to be called a proton acceptor. So this is a Bronsted-Lowry. This is a Bronsted-Lowry base, while this will be the Bronsted-Lowry acid. But what do you get from this? So these are the reactants reacting to yield products. One of the products is where the OH is now bonded to the hydrogen that was stolen. That is water basically. So this is going to play the role of a conjugate acid because it came from the parent base. And then you will have this oxygen minus the proton that it gave out, minus the hydrogen it gave out. The formal charge of the oxygen would be, valency of oxygen is 6, non-bonding electrons are 6, 1 bond on it, negative. So this acetate, we call it, would be the conjugate base, characterized by the presence of a negative charge. So again, in summary, Bronsted acids are proton donors, which is what HBr did, which is what acetic acid, ethanoic acid did. Bronsted-Lowry bases are simply those that accept the proton, which is what the hydroxide did, and which is what the ammonia did to give you products. I hope that helped.